And hey there, Calculus 2 students. We're looking at parametric equations today. What this means is we are going to look at both x and y in terms of another variable. So we're going to introduce this third variable. So for the purpose of, let's say we're looking at something like the circle, and we are going to introduce either a theta or a t, really doesn't matter, just a third variable. And you know that we can represent these in terms of cosine and sine of theta or t. And notice how we can look at not only how x is changing with y, or y is changing with x, but we can also look at how x is changing with theta or time, and also how x, or either one really, it really doesn't matter, but we can look at how either one of them are changing with time. So it gives us another way to look at them. Now this is very convenient when things move in a spherical or a cylindrical kind of motion, and that's why we're going to use them. It's going to make it easier to interpret and do derivatives and integrals. So let's look at our first example. In our first example, we are given the fact that x is equal to 2t and y is equal to 1/2 t squared minus 4. Now I could figure out how x and y relate but just by reworking this, doing a little algebra, saying that t equals x over 2, and I could say that y equals 1/2, and that would be x over 2 quantity squared minus 4. And y then would equal, this would be x squared over 4, so it would just be x squared over 2 minus 4. And this one happens to be that my x and t, my y and t happen to look the same in here, but y looks the same whether I have both my x or my t, really doesn't matter, but that's not normally the case. It just happens to be for this one. So let's look at what this graph looks like. So here's our graph, and if I'm looking at this graph, x versus t, you can see that x versus t is a straight line, and my y versus t is this parabola, and this is the graph of x versus y, and how these change as time goes. You can see each of these dots is just as t is changing. Now typically on these parametric equations you're going to have some sort of interval for your third parameter. Our definition of forward or positive orientation means as t increases, what is this doing and in which direction is it going? So let's look at our graphs of this set of parameters here. So we have x is 4 cosine 2 pi t, and here's the graph of that. You can note the dot is where I just moved my t forward just a little bit so you can see how these dots are moving. My xy plots are going in this direction, so that you would say that the positive orientation of this is in the counterclockwise direction, is how you would state that, because as t goes from 0 to 1, it starts at this point 4, 0, and moves around the circle, and then actually ends at the point 4, 0 when t is 1. And if I go over 1, I'm just going to go back around the circle again. Alright, I'd like to eliminate the parameter t just to see how x and y relate. I'm going to pull a little trick here. I'm going to look at and see what x squared plus y squared equals. Well, I know what x is. He's 4 cosine 2 pi t. So let's square him. Quantity squared, and then we'll square our y and just see what we happen to end up with. Sine 2 pi t. We'll do our algebra of this. And working this with just a little bit of algebra, I see that this thing right here equals 1. So I have x squared plus y squared. This thing in terms of just x and y equals 16, which happens to be the equation of a circle of radius 4, and that's exactly what I have. In example 3, we're looking at a turtle that is walking counterclockwise, starting at the point 4, 0. That's convenient. We just did one like that. But we need to make sure that we have the correct angular frequency in here, and that is related to this one lap in 30 minutes. So first up, I know that x equals 4 cosine that angular frequency times t, and y equals 4 sine that angular frequency times t. Now let's note that when t is 30, here is where t starts off when t is 0, and then when t is 30 we want to be back around at the beginning. So that means 30 times b must equal to 2 pi. And this just yields b is pi over 15. This gives us our parametric equations. X equals 4 cosine pi t over 15, and y equals 4 sine pi t over 15. For our next example, they just want us to write this in y in terms of x, just y in some function of x. So let's go ahead and rewrite our x to read that t equals x minus x naught over a. I'll substitute this in for t in my y equation. After a little bit of algebra, I see that we just have an equation that describes a line with slope b over a going through some point x naught, y naught. The next thing they ask us to do is come up with our own parametric equations. We can do this in many different ways. Probably the simplest way for a is just to let x equal to t, and then I would get y equal to 9 minus t squared, and if that's the case, that would mean that t would then vary between -1 and 3 since it equaled x. For the b question, it would be easiest to let y equal to t, and then that way x is going to be equal to t minus 5 quantity squared plus the square root of t. In our part C, let's look at this in terms of the parameters that we have already discussed, and let's note that if I draw a line from -2, 0 to 0, 3, and I want to parameterize this xy relationship, introduce a third variable, let's note that the slope of this line is 3 over 2, where it's the change in y over the change in x. And if we remember back to our equation, we had y minus y naught equals b over a x minus x naught. So let's now write this as x equals, and our x naught is -2 plus our x part of the slope is 2t. Our y value is, we're going to write this one as our y naught for this point, which would be 0, and then our b part is plus 3t, and that is where they got the parameters for this part of the graph. For the other part of the graph, let's note that we are writing x equals, and our x naught value at the start of this, and it had to be worth mentioning, which I didn't mention, that my t, they told me, ranges from 0 to 2, so for this first part that would be from 0 to 1, and the second part would be from 1 to 2. So how this t is going to need to range. So let's look at my a value. My slope for this side is going to be -3 over 4. So my x part of the slope, which would be 4t. Now for my x naught, I need for my x to be 0, and when t is 1, we have a 4, so this needs to be a negative 4. In order for my t to be 0, let's make sure that when t is 2, I get a 4 here for my x, and if I plug in a 2, I do get a 4, so that works. Y equals, my y part of this is minus 3t because of the slope portion. Now when t is 1, my y needs to be 3. So in order for that to be the case, this would need to be a 6, and that is how they get those parameters there, and make sure it works for either end of your points. In my next example, I am given a bicycle, and we're looking at this bicycle path of light on the rim of a rolling wheel is a cycloid, and here are my parametric equations for that. Here's my x parametric equation and the y. In graphing these together in terms of x and y, they told me to use a graphing utility with a equal to 1. Here you have it. On what interval do we get one arch? You'll notice it happens from 0 to 2 pi. So that would be on that particular interval. Alright, we now have parametric equations. X equals a cosine cubed t and y equals a sine cubed t, all going from 0 to 2 pi. In graphing each of these independently, you will get these two graphs. Graphing x and y in terms of each other without that third parameter, we would need to come up with some way to I'm going to pull that little trick that I did before where I looked at x squared plus y squared, but since this is a cubed, I'm going to look at x to the 2/3 plus y to the 2/3, and I'm going to see what that equals. I'm just going to plug in cosine cubed t to the 2/3 plus sine cubed t to the 2/3. With this, I will get cosine squared t plus sine squared t, and then I would note that this equals 1. Therefore, I have x in terms of y written as x to the 2/3 y to the plus y to the 2/3 equals 1. And this is another way to describe this asteroid. Example 8, we are using theorem 11.1, the derivative for parametric curves. Note that if I want to find y prime, I'll just take the derivative of y with respect to t and divide it by the derivative of x with respect to t. Very handy and very nice theorem that we're using here. So for my a part, let me fix this. Alright, for my a part, I'll need the derivative of y with respect to t. This is going to be 2 times 1/2 t to the minus 1/2. So this is just going to be 1 over the square root of t. Derivative with x with respect to t is just going to be 1. So derivative of y with respect to x is just going to be this deal over 1. So it's just going to be 1 over the square root of t. And that is my derivative. Same game I'm going to play here. I need to know dy over dt, and that is going to be 16 cosine t. Dx over dt is going to be equal to negative 4 sine t. If I want to know dy over dx, that's just going to be 16 cosine t over minus 4 sine t. And this gives me negative 4 cotangent t. And looking at the graphs of these, you can see our x and y in terms of t only, and this graph is y in terms of x. It's interesting to note this sine and cosine function. Notice that it is the equation of an ellipse with my slope at any point along the curve being negative 4 cosine t. And this concludes 11.1. If you have any questions, see me at the Collaborates. Thank you guys.